It's been an exciting and interesting 3 days, right? Very informative and thought-provoking. And I think it's very apt to be kind of ending up with a discussion on calculus, right? So we are here today on a panel discussion. We're going to talk about how should calculus be taught. Let me start off by introducing our panelists. We have Praveen joining us from University of Illinois, Urbana-Champaign. Praveen's research focuses on teachers' special content knowledge, aiming to provide students with opportunities to engage with mathematics rather than simply listening and following instructions. He incorporates insights from the history of math, both Indian and global, to highlight the evolving nature of mathematics. Apart from research, Praveen also teaches courses in curriculum and instruction. Here on the stage, I have with me Dr. Aekta Agarwal, who's a faculty member at IIM Indore in operations management and quantitative techniques. She has over a decade of teaching experience teaching calculus. She specializes in applied mathematics, focusing on numerical algorithms for partial differential equations and non-local hyperbolic conservation laws, with applications in traffic flow, crowd dynamics, opinion dynamics, and supply chain management. I have Mr. Sanjay Sinha here on my left. He's a seasoned mathematics educator with over 30 years of teaching experience. In the last 23 years, he's been teaching at Sanskriti School in New Delhi. Mr. Sinha's contributions extend far beyond the classroom. He has been actively involved in the NCERT curriculum planning and textbook development for grades 9 to 11. He's also trained several math teachers in India, as well as more than 100 teachers in Bhutan. We also have Dr. Rajpal Singh, who's Deputy Director, Directorate of Education, GNCT of Delhi. He taught mathematics to secondary and senior secondary students in Delhi government schools for more than 20 years and has been a principal in the Directorate of Education in the last 5 years. He's also been a resource person for mathematics teacher training programs. He's helped with curriculum development at secondary and senior secondary levels for both NCERT and NIOS, right? So we'll get started. I will start off by calling upon Praveen. Praveen, based on your research, your work, can you help set a context for us, right? Both about calculus and teaching of calculus.
All right. Good morning, everyone. Thank you for this opportunity. To talk about the context, I would like to start with a scenario. A few years back, when I was teaching the cardinality of sets in a real analysis class, I proved to my class that the cardinality of the set of all natural numbers is equal to the cardinality of the set of all integers. One of my students said, but the Z is bigger than N. Another student said, yes, N is a proper subset of Z. Then I replied, but there is a bijection between them, and that's how the cardinality is defined. To be honest, I wasn't happy with my response as a teacher. I was thinking, why is that confusion? So I was, who made this definition? And how did mathematicians react? Was there any disagreement or agreement? What kind of things were there? So I was thinking about mathematicians in the past and history. Uh, and also, what do we need to know as a teacher? What kind of knowledge I need to have to address such questions in classrooms in an effective manner? So in this discussion, I emphasize the fixed nature of math many times that highlight in our teaching. And then I will explain 3 instances from history to show a different nature of math that could be helpful sometimes. And then I will define what teacher knowledge is and how history can benefit different kinds of teacher knowledge. So the history of math will show the nature of math, and the history of math again will benefit the teacher knowledge that I will talk about briefly. So our teaching can highlight math as static or math as dynamic, showing knowledge evolves over the time. Some research highlight benefits of connecting teaching with contexts that led to math concepts in different civilizations in the history. And when I say context, it's not only India or West. all civilizations across the world illustrate this thing. And different cultures, even in single country, such as math knowledge in different languages, such as Marathi, Tamil, and Sanskrit, from the history of math. And also, there is a human face of math. For example, real human beings were involved in mathematical development. There were a lot of disagreements and agreement if we see in the history. So I want to start with one of the moment in history that could be interesting for us who are teachers and teacher educators. So consider the dilemma of one of my students who disagreed kind of that the size of n is equal to the size of z. So the idea of bijective sets in mathematics that suggests that they are of the same size. And another idea by Aristotle, part whole axiom, that says that the whole is greater than its part. So these are contradictory. And you can see this thing from this one example. So one of them is supported by one of the mathematicians who's Cantor, and the other idea was supported by Bolzano. So, but Cantor's idea dominated over the other idea due to certain reasons, and but that doesn't mean the other idea is wrong. There is research in math. For example, this research by Bensi, and they adopt part whole axiom, the Aristotle's axiom idea. So that's how like they are defining the other idea as well. So the knowledge of the presence of such debates in the history, such as from Aristotle and Bolzano to Cantor, so that might help teachers walk into students' shoes. Think about the scenarios again, like what my students asked. My student was not quite wrong. I might had responded in a better way using this particular historical example. So there could be alternative ways in history to define a concept. So moving to a different, another example, this is also an interesting example that can also help us see the evolving nature of math as a discipline. Uh, Howell and Darboux, they were French mathematicians, and had requested feedback on his first draft of, while he was writing a book on differential calculus, he wrote to Darboux and asked him his feedback. But through the correspondence, I won't go detail in more into detail into this thing, but I want to highlight one thing. So in this correspondence, Darboux provided counterexamples, and he wanted to convince Howell that he needed to take more care in his proofs. So you can see the language in these, like in this language, this highlight there is a kind of disagreement between these two mathematicians, and you can see like the words, the choice of words, like you have not addressed the nature of my objection. If there is lack of rigor, your proofs are not proofs actually. So there is a kind of a debate kind of among these great mathematicians. Uh, Moving to the third and final moment from history, which is from Yukti Bhasha, which is 16th century text from Kerala. So this could be a powerful resource for our math classrooms in calculus. And you might see like some of the things that I have bolded. And on the right side, this could be seen in modern notations we might understand. So they're actually proving Gregory Leibniz theorem, which we study in calculus, and you might see the language they are using, some of the language that connects to the idea of limit. And this could be interesting, how and what kind of words they're using for limits, and were there any cultural influences in how in understanding how they were making sense of the idea of limit. So all of these three examples, they are likely to support what we need to know as a teacher to highlight math as evolving, and we might value our students' ideas rather than labeling them as wrong, and offer them opportunities to contribute in the class. So, but what is teacher knowledge? So This is one of the popular models to identify and measure teacher knowledge in mathematics. So one of the important things in this picture, if you see, like the distinction between subject matter knowledge and pedagogical content knowledge. So for example, I might be good at proving math theorems. I might be good at subject matter, but that doesn't necessarily make me a good teacher. I need to know more than that, uh, just knowing the subject matter. So that is what like pedagogical content knowledge is. And we do not necessarily talk about pedagogical content knowledge. For example, teacher training programs, and history can offer us support in these teacher training programs to enhance our teachers' pedagogical content knowledge. For example, sometimes I can sequence the content, how I'm explaining in my classrooms, motivated by history, how they were developed over the time. And also, I could have better respond to my students in the scenario I just explained earlier. So in my research, I try to investigate how we in calculus and real analysis classrooms, how we might encourage our students to view math as an evolving discipline from history and to the future. So, and how they might contribute in the classrooms in terms of sometimes discovering some discover opportunities, and which can help them position themselves as agents in the classroom. So yeah, so I think I stop now, and yeah, and we can discuss more about it after other panelists discuss their ideas.
Thank
Thank
you
you.
so much, Praveen. In fact, we will be talking again and again, so don't worry about. So, in fact, the idea of knowledge required for teaching has been a recurring theme in the conference actually since the day one, since the keynote, through a few workshops and paper presentations and discussions. Even yesterday's panel discussion spoke about it. So, I think it's a good opportunity to actually segue to a teacher with over 30 years of experience, right? When it comes to math teaching, Sanjay, we all know the syllabus load and time crunch. Within, with the background of these constraints, how how can you do justice to teaching of calculus at the school level? Could you share your thoughts on that?
I'll answer your main question a little later. What I would like to do at the moment, that I would focus on what is happening currently in our schools, how the calculus is being taught. And in my teaching experience, what I have found is that while introducing some ideas or some concepts of calculus in schools, we normally define certain concepts in a manner that we do not give them the right picture. And then students tend to mess up when they go for higher classes, go for higher studies in maths in colleges. I would like to cite some examples from what I have just listed. I would like to begin with the idea of some concepts in pre-calculus. For example, the limit of a function when x tends to a particular point. The kind of definition that we give to the children when we have limit of a function when x tends to c, it raises lots of doubts. You say that the limit of the function x tends to c is the number L when fx tends to L whenever x tends to c. There are many doubts in the minds of the children as to how close the x would be to c. Whether x will take finitely many values and remain close to c, or will take infinitely many values will remain to c. Will it ever become c? And whether the function fx will always approach the number L, or will it become ever L? So lots of doubts are there in the minds of the children. What we do normally to the children when we introduce the idea, we take an example of a function, say x squared minus 4 upon x minus 2, and we display some values, two sequences, where we tell them that x is approaching 2 from the left-hand side, taking values 1.9, 1.99, 1.999, and so on and so forth. And then we look at the corresponding value of the function fx, which seems to be approaching the number 4. And one more sequence that we give that kind of takes values which are larger than 2 and remain very close to 2. And then we look at the corresponding value of the function, then we find that the function remains close to 4. And then we ask the children to conclude that the limit of the function when x tends to 2 is equal to 4. So in a way, we are trying to give a wrong notion to them that if x approaches the number 2 over 2 sequences, just 2 sequences, and we try to look at the behavior of the function approaches the number 4. And we ask them to conclude that the limit of the function when x tends to 2 is 4. I'll give you a counter example, like this example of function. Suppose fx is given by 1 if x is rational, and if x is given by -1 when x is irrational. We can have 2 sequences displayed. X approaching 0 over the sequence 1 upon 10 raised to the power n, and the corresponding value of the function always will remain 1 because 1 upon 10 raised to the power n for every value of n will remain a rational number. And therefore, the corresponding value of the function is always 1. On the other hand, again, when x approaches 0 from the right-hand side, taking values 1 upon 10 to the power n, where n tends to infinity, the corresponding value of the function also remains 1. So going by that logic, should we conclude that the limit of the function when x tends to 0 is 1? Because over 2 sequences, we find that x is approaching 0 and function remains 1. Here is another sequence over x is approaching actually 0 once again. That is root 2 upon 1, root 2 upon n. So we find that x is actually approaching 0 when n tends to infinity. Root 2 upon 1, root 2 upon 2, root 2 upon 3, root 2 upon 4, and so on and so forth. In that case, each value of x happens to be an irrational number, and therefore the function will always remain -1. Hence, the limit cannot be 1, which we concluded earlier, going by the logic that x was approaching the number 0 over 2 sequences, and function was approaching. In fact, function always remained 1. Therefore, there is a need to emphasize over the correct definition. This definition that we give in grade 11 at a school level is a very intuitive definition and it lacks actually rigor. It lacks rigor. Therefore, we are not able to prove any theorem based on this particular definition. We should emphasize over the fact, I'm not suggesting that we should give the accurate definition of limit of a function at a point, because this will be the level where the children won't understand the exact rigorous definition. But there is a need of telling them that the function will approach the number L, or function will have the limit L when x tends to A, in the situation that every sequence which converges to the point C, the corresponding sequence must converge to the point L. So the condition is not that there are only 2 sequences over which the function, x will approach the number C, and the corresponding function actually should approach the number L. That is not the precondition or pre-requirement. The actual requirement is that whenever the condition is here that for every sequence xn, with xn not belonging to domain of F minus the set containing C, which converges to C, the sequence fxn must converge to L. That is the precondition that children should be told. We should also tell them that we are in a way giving them the sequential definition of limit. There are actually 2 definitions of limit. One is called, popularly known as epsilon delta definition, which is actually introduced at a college level. And at a school level, there is no definition. In fact, we have a very vague definition, and that leads to misconceptions. I would suggest that epsilon delta definition should also be somehow discussed with the children. And at least in words, we should say that no matter how small a given positive number epsilon is, we can find a small enough positive number delta such that whenever x is within delta distance from C, fx is within epsilon distance from L. This is the most appropriate definition. In fact, there is an equivalence of the two definitions, sequential definition of limit as well as the epsilon delta definition of the limit. But this is missing from the school level. What I'm trying to suggest is that we should tell children that the precondition is very different from what we give them. This is again another idea of pre-calculus, and we normally introduce this myopic definition of composition of functions in this manner. And we say that if f is a function from A to B and g is a function from B to C, then composition of f and g is a function from A to C such that g circle f of x becomes g of f of x. And immediately after this example, we give examples of the kind non-negative square root of x plus 1. That it is a composition of x plus 1 and root x. But if you give a very closer scrutiny to it, you will find that x plus 1 is a function from R to R, whereas root x is a function from the set of non-negative real numbers to the set of non-negative real numbers, or maybe from the set of non-negative real numbers to the set of real numbers. So there is a mismatch. Immediately after giving the definition, you cite an example where the domains are not exactly the way definition says. Definition says f is from A to B and g is from B to C, then composition of g and f exists, sorry, f and g exists, and that is from A to C. And under root x plus 1 is not the exact example that you have cited. In a similar way, when we come to calculus and introduce the derivative part, and we say that limit of f of a plus h minus f of a upon h when h tends to 0, if this limit exists, this is the derivative of the function at a. And there is a sentence quoted there in the bottom of it. Observe that f dash a quantifies the change in fx at a with respect to x. I have a slight disagreement with the line that is written there at the bottom. F dash a does not, according to me, f dash a does not quantify the change in the function. It actually quantifies the instantaneous rate of change of the function. The word instantaneous rate of change is missing from there, and that leads to, again, some kind of a misconception. But the reason why I brought this definition up at the moment is not this reason. Recently, I was in a discussion with a very high-profile members, and a very senior member commented that in grade 11, we are only doing right-hand derivative. We are not doing left-hand derivative at all. And Dr. Rajpal Singh is a witness to it. When we go to grade 12, we define derivative in this way. F dash a is equal to limit of f of x minus f of a upon x minus a when x tends to a. If this limit exists, that is the derivative at a. And we can always establish the equivalence of this limit with the earlier limit that we gave in class 11. Immediately after that, we say that this limit would exist provided the right-hand limit and the left-hand limit both exist and are equal. The right-hand derivative actually is limit of f of a plus h minus f of a upon h when h tends to 0. That's the right-hand derivative, and the left-hand derivative at a is actually the other one. But when we compare the right-hand derivative, it somewhat matches with the definition which was given in grade 11, and that leads to the confusion that this was only right-hand derivative. So there is a need of emphasizing on the fact that h could be even negative, h can approach 0 from the left side also. That part is not written anywhere in the textbook. It simply says that h approaches 0. I'm not saying that textbook is wrong. What I'm saying is that one should interpret the fact that h can approach 0 from either side, and therefore, even grade 11, we are talking about both-sided derivatives, not just right-hand derivative. So that was the reason I thought of bringing it here, that we should also talk about h approaching 0. When I say h approaches 0, we have to say that h approaches 0 from either side. Then I prepared an applet on GeoGebra where I have taken h also negative, and I've kept h negative and made h approaching 0. But if time permits, I'll display that GeoGebra applet to you later on. Even the second applet that I have come up with, where I have made a connection between the function and its derivative and how the graph is behaving with an example with the help of the GeoGebra. Now, this is another topic which is very much confusing, because people are thoroughly confused whether we should conclude whether the function is strictly increasing over a closed interval or over an open interval or over a semi-open, semi-closed interval. So if time permits, again, I'll come back to this later. But I would like to emphasize on the fact that the function can still remain strictly increasing over the interval or over the entire real line, even if there is a point where derivative vanishes. But textbook seems to suggest that if derivative vanishes at a point, it cannot be strictly increasing over the interval. Firstly, I disagree with the word increasing function over interval, because increasing function over interval has the following criterion, that x1 less than x2 must imply that fx1 is less than or equal to fx2. So this seems to be the definition of a non-decreasing function. So increasing function should be better termed as non-decreasing function, because there is a condition where fx1 can be even equal to fx2. So there is a possibility that for every pair x1, x2, x1 is less than x2, if x1 remains equal to fx2, then how is it increasing? That will be a constant function then. Are you getting my point, what I'm trying to suggest? But strictly increasing function, they say that x1 is less than x2, then fx1 must be strictly less than fx2. So here is an example of x cubed, which is a strictly increasing function. But all of us, most of us, will differ from this and will say that no, it is not a strictly increasing function because there is a point where its derivative is 0. So that theorem is wrongly interpreted. And then we come to this conclusion that the function is not a strictly increasing function. It is actually simply increasing function. So there's a need to talk about this also. This is an example of a function x minus sine x, which is clearly strictly increasing in the entire interval from 0 to 4 pi. But there are points where derivative is actually vanishing. There are points where derivative is actually 0. So it's an example of a strictly increasing function. Similarly, in maxima minima, when we talk about, we deal with the problems of maxima minima, and there we normally apply second derivative test to conclude that the function is maximum or minimum at a point, and we use actually second derivative test. Second derivative test is meant for local maxima, local minima. So why is the word local dropped? That's not suggested anywhere. So I took an example where finally we have applied the second derivative test. In fact, first derivative test, there is no issue at all. But second derivative test, when you apply, then you find that there is only one critical point. There is only one turning point. And that is why we are allowed to drop the word local, because that point becomes a point of global maximum or minimum. Like in this case, what is happening that at x equal to a upon root 2, the function becomes local maximum because the second derivative test says so. But the word local is dropped because there is only one turning point. So the function has to be then globally maximum at that point. So this particular idea is missing from the textbook. Once we deal with second derivative test, there we deal with second derivative test for checking the points of local maxima, local minima. On the other hand, when we come to the application problems, we just drop the word local without giving any reason to it. So reason must be given. We deal with this implicit function and its differentiation. We do it mechanically. We just tell them that if you are not able to express y in terms of x explicitly, just differentiate both sides and get the derivative. But there has to be some idea behind this implicit differentiation as to why we are doing implicit differentiation. Does the function exist? Do we have the derivative of those functions? So I am trying to clarify it with the help of this particular example. Like x cubed plus y cubed minus 9 times x times y equal to 0 has a graph. If you consider it is the graph of one particular function, that is not possible because it does not clear the vertical line test. For a given x, you can see there are more than one values of y. So it cannot represent one single function. So you have to imagine that this is a union of actually three functions, as noted there on the screen. One part is f1x, the second part is f2x, and the third part is f3x, and all three of them will invite derivative. And that is where the implicit differentiation comes in. So we just differentiate both sides and we go for differentiation. Then it becomes meaningful for the children as to why we go for implicit differentiation. Otherwise, what we do, we just tell them that, look, y cannot be expressed in terms of x, find dy by dx by using implicit differentiation. Last but not the least, because there is a paucity of time, I would like to highlight on the fact that sometimes, in our teachings, we should involve this kind of working, sometimes display this kind of working and come up with an absurd result and ask children where actually we are going wrong, so that we are arriving at a wrong result, like pi equal to 0. So this will be a food for thought for you. I picked up from a LinkedIn post. Of course, there was no answer displayed there as to where we are going wrong. But it's very interesting to note as to where we are going wrong. Look at the function fx, which is tan inverse x plus tan inverse of 1 upon x. Derivative is obtained by using addition rule and chain rule. And derivative turns out to be 0. And there is a conclusion that the function should be a constant function. And hence, f of 1 should be the same as f of minus 1. And that leads to the absurd result pi equal to 0. So it will be a food for thought for you. You can also find out the error from here as to where we are going wrong. And with this, I want to conclude.
Thank you so much. I think your examples were they were exemplifying MKT in action, right?
Yeah.
The teacher has to challenge, question, reason, and understand for herself before she can do justice to teaching in the classroom. It was nice how you spoke about what we typically do, the misconceptions that rise in the child's mind because of that, and also gave us an example of how differently you should be doing this, right? So taking up that point on misconceptions and gap in understanding, typically they surface at undergrad level, right? So Professor Aekta, your students, your group of students are mixed, right? You have students who take mathematics out of, what do I say? They do want to pursue mathematics and some don't. How do you handle this case where there are gaps in understanding in your classroom?
Just to give a little background, so I work at IIM Indore and there is a 5-year integrated program which is known as IPM. Many of you might be knowing about it. So it's not a BBA, it's a Bachelor's in Foundation of Management, where except physics and chemistry, we teach them everything from maths to dance, right? So it's like a kind of a cool liberal arts program along with the aesthetics of maths, stats, coding, economics, sociology, so psychology, everything, right? Because generally business is for people, by the people, and therefore the problems should contain of all the aspects. So the idea is that we get students who, let's say 80% on an average, are students who are JEE, LN or whatever inclined, and we have 20% or let's say 15% students who have left maths after 10th, right? Either for the love of other subjects, for the relatively more love for other subjects, or by the phobia or by whatever what they face. So I will just I think that's easier to read. So I will just say some of the problems which I fear. So whenever I start my class, I try to divide my class into through very informal introduction of the students. Just classify them as I love math, I hate math, I can bear it and I don't care, right? It's just that it's in the curriculum and I have to deal with it, right? So the problem is, this idea is not to classify them like we do in schools, generally the dummy schools, but for me to understand that who are the kids who need me psychologically, emotionally, and inclusively. So when I talk, the feedback which I get from students, that ma'am does not like science students, and I'm a applied mathematician and a CFD person, right? So my idea is to know the people who need me, right? So then the problem there is that before how, they ask why do we need to study that? And that's the thing from even science students, let's say. Then the phobia of someone else running faster than them running along, right? They're always in that peer pressure of the relative rat race or cat race or whatever race we want to call it, right? They're always fear of me running slowly, right? And they don't recognize their power of social sciences, their power of reading through the text, but they are always, there is a phobia of someone doing 100 questions of R.D. Sharma or P.K. Garg or whatever, and I'm not liking it. I don't get the dopamine of my day from that. So that's their problem. Sometimes people think that they know how, and this is the problem with the dummies which we get from school and coaching. I'm sorry if I'm using that word. I think I can use it here, right? Because we are facing all of these problems. They think they know how. And with all the good schools coming up where people are motivated and they want to teach change the way how maths is taught. So over the time in 10 years, I've seen that there are changes in way the students are taught the way I want to teach them, I would have taught them. But still, the people who are going to, let's say, coachings or doing 10 years of JEE ka papers, LN ka papers or whatever papers, they think they know how. And that's a problem for me because there's a lot of ego. You understand? I don't have ego, but they need validity that I have done 4 years of LN, I have done 4 years of JEE, and she is coming and telling me that what they know is, no, I never say it's wrong. I say, ho gaya, you have come to IPM, you have done, sab log tumhe bol rahe hain, you do this, you do this, you do this, you have reached here. Now it's time for learning, right? It's not time for coding. It's not, you're not a machine anymore. So give yourself time to learn. So this process takes a lot of time for me to tell them that they need to trust me. I have to develop some kind of psychological friendship with them, emotional connect with them, so that they trust me on this, that I know what I'm doing, right? And then they are reluctant towards both how and why. Why to hai, and ab how bhi aa gaya. So therefore, when I deal with my non-math students, they are my good kids in some sense, because they don't know how and they don't know why. And that's why they're a clean shit, right? You get what I'm trying to say? Huh? Okay, so these are the problems which I face. So what I do first is, I introduce purpose in their language they want to hear. So I want them to be on my side, right? So this is my opening class. They are business kids, right? They don't want to learn epsilon delta, though I want to teach them, but they don't want to learn. So I teach them through what they want to hear. I want them to solve a regression problem. I want them to give you see, look at the questions. I want them to design a marketing strategy. On the first day of IPM, I give them that power that you will be hired tomorrow if you listen to me and I know my job, right? I know my job, and therefore I am giving you the power to design a marketing strategy. And what are the things you need for that? You need statistics. Okay, I'm not a stats person, so I don't market it. But what I market is that I need the best fit line. First thing, I give them calculus ka line chahiye tumko. Line ke liye kya chahiye? Sets chahiye. So I give them line. Line is a function. Then you need, so ek naya term aage. They have a new term, function. So function gets the validity in their mind. Then there is distance function versus square function. Why don't I use mod? Why do I use square? So I bring in the differentiability and the smoothness of the bowl of the square function. I'd say this is corner, so you will hit hard. If you go down and reach the minimum, your ball will keep bouncing. If you have, the corner. And then some of the students don't even know what's the distance. They're scared of the negative numbers. So I bring in the notion of the number line. I make them skip the numbers and make them design the distance, that y distance always has to be positive. So the mod comes into play. And then finally, since they need to find the distance and the minimum distance, they know that they didn't need the optimization in their kitty. So the whole calculus course 1 is verified and validated on the first day, and they don't ask me anything after that. Then they will say, ma'am, but we are management people, why do I need all this, right? But you don't need to be a dummy job sitting on a desk. You need to make a machine learning algorithm because they get more money, right? And if you want to make an algorithm, if you want to validate your algorithm, you need to know maths, you need to know stats, you need to know linear algebra, you need to know coding, and you need to be a business person to design the algorithm for that business problem. So their whole IPM ka 25 lakh rupees is justified on the first class. And I have them on my side. So they don't ask me anything. Then there are some black box misconceptions, especially with the students who have done class 11, 12 ka math is famous JEE question, 1 minus 1 plus 1 minus 1 plus 1 minus 1. So one of my students actually goes to the switch box and she keeps turning it on, turning it off, turning it on, turning it off. So, and I asked them, what is the answer? They say, ma'am, 0 if she stops. But she's not stopping. She keeps on going. And she will get 100 rupees if you stop, you get 100 rupees if she stops. What is the answer? So the answer does not exist. In the first class, they know that they get the idea of the sequence of the partial sums without naming them. And since they know that she can't stop, I don't reach the right answer. I don't give them the answer because it comes in integral calculus, but they know that the JEE mein jab the teacher had told 0, 1 and none of these, all of them are correct, it's wrong. And I get students, nahi ma'am, JEE mein Ellen wale sir ne ye karaya tha, all the 3 are correct. मैंने बोला you tell me. Then there are some students who come to me that this is 1 plus 2, 1 plus 2 plus 3 plus 4 plus dot 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 is 1 by 12, right? Because they learn string theory from somewhere, hai na? So I tell them, you tell me, if I give you 1 rupee daily, can you get an answer in fraction? Forget about 1 by 12. No, ma'am. मैंने बोला, then you are asking a wrong person, Baba. Right? You are not asking the question to Quora. That is your problem. That is not Quora's problem. Right? So I give them that, I leave those loose ends to justify that you have to learn from me. Right? Second thing, this which Praveen also brought up, sin x by x as x goes to 0. If you ask a JEE trained kid, he will say, ma'am, it's 1. Why it's 1, ma'am? Lopita's rule. मैंने बोला, but the proof of the derivative of sin x is this limit. How can you use the answer in the question? Second thing he will say, ma'am, series. मैंने बोला, how do you know that this series, what is the meaning of series? How do you know where it converges? And how do you know it converges for all x at the same number? 3 open questions, he does not know the answer. So gone. His whole Ellen ka coach, so I keep saying Ellen, they will sue me. Right? The whole coaching is gone in one day. Then 0.9 bar is 1, right? NCRT, I'm sorry, if, maybe they meant it right, but they will say let x equal to 0.9 bar, multiply it, subtract. They give me this answer very proudly, CP ke liye, they will give me class participation. I say, who told you 0.9 bar is a number? Who told you that? You're assuming that. To assume that it is a number, you need me. It's a geometric progression. Prove it, learn the convergence, and then tell me it's a number, then you go to NCRT, Baba. So, right? I have spent 3 classes in my first year college teaching and I got a feedback of 4. Because out of 10, not out of 5. Because they thought that I'm bad, right? Then you ask another question, is it integrable? Give me a non-integrable function. What they will say, ma'am, e to the power x square. Then normal distribution to ho gaya. E to the power sin x, e to the power x square, e to the power x cube. Why? Why? Because they have the power of feeling great when they integrate it and get an answer. They are looking for an answer, which we have been talking about. No. I told every continuous this function in this world is integrable. For that you need me. Need me, need me, need me, need me. You get it? Right? So, first few days you give them, you take away this power from them that they know a lot. It works both ways. Right? It will give you the power to the non-math student that we have ground to learn, and it brings you that chota sa izzat, small izzat in front of the math student that she also knows something. And there is a, space to learn. Then, some of the things I heard, like last 2 classes also, that when we are teaching functions, we should be telling them some graphs, right? And when I ask them x square, they say, ma'am, I know this graph. But the calculus is about drawing this graph. You can't draw this graph without limits, continuity, increasing, decreasing, second derivative test, and then this is the first example we should be taught to them when they know how to plot. When we do 11th, 12th, we are gifted this function as an automatic function, which is wrong. You can't draw this function. Okay. So I will try to speak less, right? So then I demath the maths. 0 by 1, right? It's 0. Talk to them in terms of people, pizza, happiness, movies, girlfriend, boyfriends, whatever the language they understand, not in terms of fractions. Tell them why it's 0. Again, why is 1 by 0 denied to exist? Right? Of course, there is that example of cross-multiplying and say and all that. But I say, for example, if you have all the money in the world and you have no one to share with, right? They connect. The poor kids have been studying all life and they have no happiness is undefined. They don't know where to find happiness. So they connect, this is a psychological thing which they give. So it might be infinity. Then comes infinity. What could be infinity? Ma'am, it's inverted 8. Ma'am, it's a number. Ma'am, it's not a number. I say it's a perception, right? It's a perception. Talk about Priyanka Chopra, upper ceiling. There is no upper ceiling. Skyscraper. Then there comes infinity minus infinity, ma'am, 0. Ma'am, infinity, because thanks to Cora, right? I say my infinity, since it's a perception, my infinity is Harvard, let's say, okay? And your infinity is I am Ahmedabad, because you're already at I am Indore, no? So I am Ahmedabad. How can your infinity and my infinity subtract, you get 0? It depends that how my perception is larger than you, because you would get a G and your number should be greater than every G above that. So since my perception is not equal to your perception, infinity minus infinity is undefined, because it depends where you stop. And that's it. They understand that it's indeterminate, you know. Yeah, so then function, okay. So I will take some anecdotes. Function. My God, if you ask in the first class, domain, subdomain, oh no, codomain, unique image, unique sab bhul jate hain. I say, what is your most natural process in this world, which is without which you won't exist? Reproduction, right? Reproduction is a function. Every son has a biological unique father. 2 sons can have only one biological father, and 1 son cannot have 2 fathers. Ho gaya function. They never forget it. They never forget it, because there is no unique image, no unique pre-image, no all that drama, right? You teach them in first class, they feel so much, they laugh, of course, right? Reproduction is a sensitive topic, right? So everyone laughs, but they feel empowered that they have learned something in which they don't have to cram. And then I let them come with the formal definition themselves. I never write the definition on the board, right? Then this is, you can play, Ganesh, if you have time, you can just play. So again, don't force them to plot. Plotting is the last exercise of calculus course, right? You tell them, ask them this question that, okay, that why x square can't be both of these. They will say, take points, keep joining them. How do you know that it can't go up, it can't go down, why it has to be smooth? Continuity, differentiability, minima, maxima, decreasing, increasing, all is included in that. There is a GeoGebra video which Ganesh is missing, can play. But if you play this, you can show that GeoGebra can plot ... for you, and these dots are not enough because you can't join them. R is dense, we give them that power. Leave R is dense in air for the people, for the JE people to have that dopamine from the class, right? Then, this sir was also talking about these 3 functions. Tell them, make a story around it. What is the difference in these 3 functions? First thing, you can't divide 0 by 0. So you are enjoying, right? Your happiness is increasing continuously. But at x equal to 0, your happiness remains smooth. At 0, suddenly you become 0. At the second function, you are not even there to enjoy that happiness. At their x equal to 0, your friend orders a pizza, so it becomes 100. Right? And then they know that as x goes to 0, why these 3 limits should be same, right? Again, make human exercises for functions. For example, since they're business kids, I take the tax lab and I tell them, without even introducing what's a piecewise function, I tell them to bring a function and introduce the nuances of comma, less than equal to, this table, that table, because they feel it that they have done a business case. Similarly, when I'm introducing continuous function, breakpoints, and so on, I bring them a question from a canteen where they're feeling that they're following a business problem and trying to reach a value of price where there is an equality between whatever the profit and whatever game, right? So it's like a game. So we call this case study teaching. So you have to introduce cases at each point without overwhelming them that they are doing a mathematical concepts. So this I've already done. Infinity. Choose words like sky, earth core, glass ceiling. You're not allowed to come back. Work with sequences on GeoGebra. Also, like sir was saying, that the language which you use, if n is going to infinity, you are becoming larger. No, it's other way around. You are allowed to become as large as you want if you drag your n enough. So how do I tell in story? Because they don't want to learn definition. You want to reach IIM Ahmedabad, that is your infinity. How much larger you have, how much it's enough to study so that you cross that bar line of Ahmedabad. So your aim is to cross IIM Ahmedabad, that is your G. How much you have to study that you cross IIM Ahmedabad. Your G becomes less, you have to study less. You don't need anything in life, don't study only. You need Harvard in life, study more. So first you decide your perception, your glass ceiling, and then work n enough. Once you have crossed an n, you are always going to surpass that line. So once they are in that context, they stop me whenever it's my mind, right? Then again, going to Sir point, finite limits, right? We don't want to teach them delta epsilon, right? We don't want to teach them. There is a game, there's an applet on GeoGebra. They just play games, right? So again, I play games with my kids in class. From the last MTA conference, I came to know about GeoGebra. Before that, we used to take chalks in class, and we say, I want to hit RVM, Ramanujan sir, I want to hit him, and I describe a distance around him. How much do I have to move that I hit the target? So I've already decided my epsilon distance, and then I back engineer my delta distance around that sea. And then they play games, they hit chalks, we go to garden, and we do all those things. But then, thanks to MTA, I came to know about GeoGebra. I don't get sued for hitting people now. And therefore, I can apply these finite limit games where it can decide that your pink and green region have to intersect around that point C, and you can decide on delta not good, delta good, keep playing with epsilons. And I never introduce formal definition in my class. My kids come with a formal definition. Why every epsilon? I always say, to prove a theorem, you need every person of your class to be good. That is the ultimate truth. But if you want something to be false, you need one crocodile in your river to make it bad, right? And that's how they come with counterexamples. Then this is series. People are confused why summation 1 by n becomes infinity. There is this special 3 blue, 1 brown series. There is this leaning tower of liar where they go to the carpenter guy, and then they cut the things, and then they do this thing, and it never falls. So kids enjoy, right? Kids enjoy. Last thing on my end. So now for my case story of Riemann integration, right? Again, this is the where MTA gave me power last time to think on those lines. But I give them this case study. I give them that power to design SBI ka interest SBI in my virtual world. Ki optimal interest policy. So your bank account looks like this. You are the CEO of Amazon. You are dealing with the bank. If this is your bank account, how should your interest look like so that it is useful to both the parties? So you have to come to an optimal solution. So you see, I've given them the power. They will say minimum hoga, minimum. So now they don't know compound interest. Every ninth kid knows simple interest at least. Simple interest needs a common principle throughout the time. So if you talk on a common principle, you are very biased because either you will maximize or you minimize. So the first step comes, divide your time into separate khachas. On each khacha, you are allowed to choose only one principle. Once you know one principle, you have only taken that kind of Riemann sum comes later. Don't do the naming now. Interest, and you sum it up. But do you want to stop? I make them calculate all these things because they want to use the best interest. But what happens is when they calculate it, they say, no, let me increase n more, increase n more, increase n more. There is no upper ceiling. So n goes to infinity. That becomes my Riemann sum ka definition. And then I say that it is Riemann integrable. This question can also be used to say that how does discrete probability becomes continuous, discrete average becomes continuous average. Right? Continuous average increase and integral. Because if I want to say average temperature throughout Bangalore, I don't know what is the smallest interval of the time on which I should be recording my temperature. I should record every instant, therefore n has to become infinity, and therefore it is the integral of the function, and you can also bring interpolation and all those things, right? So you can use GeoGebra again to do this. One more example is, like all, why they always look for men, why formal definition first principles is so important, because they are the repository to create numerical algorithms. So one thing I tell them in the first class, that why some calculators are so pricey, some calculators are cheap. Why? Because you as a business manager, you need to decide the price of the calculator. So if you are saying that if I am taking e to the power sin x as the thing which I want to integrate, I want better approximators. Better approximators will come through my good friends, which are polynomials. That is why you need polynomials to make Taylor. But then that you have to know that the Taylor converge. Once the Taylor converge, there is an error term. You need to minimize that error term to maximize your profits. Therefore, as a mathematician, as an algorithmic trader, you need to know ki why do you need interpolation ka always the error, why Taylor approximation theorem is so important. So now their whole kahani is clear. They want to become CEO of some Casio. For that they want to minimize the error. For that they need Taylor. Taylor के लिए मुझको क्या लगेगा? Series लगेगा, functions लगेगा, differentiability लगेगा. Again, when you want to make these approximators for numerical analysis, right? For derivatives, first principles. Because you want limit h tends to 0 on computer, you cannot go to limit h tends to 0. Therefore, you need an algorithm. The first algorithm is ready, right? Okay. So closing the loop, right? So more emphasis should be on the emphasis and the impact of the hypothesis of the theorem. Before writing the theorem, we should analyze the hypothesis. What do you need? Let the kid come himself through the hypothesis, showing calculus that it is real. You do a lot of case-based learning, like I already explained. You give them a lot of power by giving them responsibilities in terms of reward coming on the board. Sometimes people are shy, but in my class over the time, people come on the board. You give them a lot of power. You give them a lot of, assurance that they are doing right. There are a lot of other resources like Kahoot, right, for in-class quizzes. There is Starcia Grid and mind mapping. You take out the fear from them. Therefore, you have to be humble. You have to be inclusive. You have to spend a lot of time with them, not teaching them, just being there for them. Therefore, you need to give them emotional and psychological contact that you exist for them. You are not hand-holding them. You are just existing for them. And you will run along for them. They don't need to run faster because their teacher is running along with them. And then accept. This is a very big problem, that teachers don't accept that they are wrong. And they think that, sometimes they think that they're Einstein and they have some power over the kids. You need to say that, as a teacher, I might be wrong, you might be right, and I will come back to you next day, or depending on how your involvement with the kid is, say that, give them that power through their psychological context. And this, I think I will, when you ask me the next question, I will ask you that.
Thank you so much. We've heard a lot of examples, both from the school level as well as the undergrad college level, right? A common narrative, of course, in India is that, yes, we have few islands of excellence, but the scale, when we talk about Indian education and math education, is daunting, right? So Dr. Singh, you have an experience both as a teacher as well as an administrator. So if you can tell us how, when we talk about government schools in India, what can we do to do justice to calculus teaching?
Good afternoon, everyone. How to teach? Definitely we are talking. But there is another thing which is embedded with this, why to teach. And these two statements are from the perspective of a teacher, but at the same time, perspective of a student is how to learn and why to learn. I'll share you a data, as ma'am is talking about government school and blah blah. Last year in 2023-24, 1,60,800 students cleared class 10th examination. 23,700 opted for mathematics in 11th grade. That is around 15%. Is there anybody here from government setup? 1, 2, 3, 4. So, beyond CBSE schools, if you talk about CBSE school, Delhi is the only state where state government schools are affiliated to the board. Otherwise, in other parts of India, state government schools are affiliated to the state boards. So, students, those who are in CBSE board, ISC, IB, IGCSE, a part of this, there is a very, very large number of students and teachers, those who are there in India. 5-6 years back, I'm sharing you something, because for almost 34 years, I have been a practitioner teacher in classroom, whether it was a secondary school teacher, then a senior secondary school teacher, being a principal also, I was a practitioner teacher, and now as a deputy director, still I am a practitioner teacher. I take my classes. See, why this is 15%? There are certain reasons which I could see behind that. 5-6 years back with Delhi SCRT, we had a research. We delivered certain set of questions to students, and at the same time the teachers, those who were teaching their students. Questions were designed for students. They were mostly procedure-based, calculative type or say procedure-based solution type of questions. And in the same context, with the same teacher, those who were teaching them, the question was designed for them, the concept behind that solution. Later on, after analyzing the data, conclusion was students and teachers, they were performing at the same level. Where students were not doing well, we find that at the same time, the teacher, those who was teaching them, he was not also doing well in that case. See how the things places in classroom. In being a teacher, 91 to 15, almost in 24 years, I have been there in 14 years for a general school, and for 10 years I was in a school which you can say a super ability type of school, or they say the school for gifted children or bright children. The very first day of class, I share you one experience. There were 100 students around that class, 3 sections, 35 each, and all were sitting in the same type of hall. And they all were bright kids. They were selected after screening from whole of the district. Everyone scored more than 90 marks in 2000, I'm talking about 2006. So at that time, board exam was of different type of exam. All 100 passed, there was no 20 marks of sort of thing. So when all this type of introductory class was over, I just thrown up one question. I said, tell me value of 1060. And believe me, when I completed my statement 1060, I got a whooping answer from anyone. Sir, this is root 3. Then I said, okay, if I say it is root 3 upon 2, could you prove my answer is wrong? Or could you prove that your answer is right, that 1060 is root 3? And out of 100 very bright children, only one student could respond, provided that at that textbook, there was an activity in the NCERT textbook which used to explain that how 1060 is root through or why sin 60 is root 3 upon 2 like that. Then I thought that how do you know it is root 3? Then I came to a very, very interesting answer. One student said, sir, my teacher told me, write down 0, 1, 2, 3, 4, divide them by 4, take square root, and these are the values for sin 0, 30, 45, 60, and 90. And then get a reverse gear. You will get the value for cosines. Then divide by sin upon cos. You will get value for 10. And then make the reciprocal. You will get value for all 6 trigonometric ratios, 0, 30, 45, 60, and 90. I was thinking of where is the trigonometry in all of this process. So they were taught in that way where there is no process of what we were saying, or why do we reaching to the conclusion of that research, that why it is happening. And one more example, that was from a lower class. I was assessing some project in a very elite school of Delhi. That's not an example of government school. Very elite school of Delhi. It was 7th or 8th grade. Project 4-5 kids, very effective communication. They have a project on area of rectangles, squares, and project. They had a creature of a building, and they have created the area, then its cost and paint cost and construction cost, everything based on the area. So I generally, just what I asked, tell me what is the area of rectangle. So they said, sir, this is length into breadth. Okay, then as Mem was saying down, how do you know it is length into breadth? And they said very innocently, sir, Mem ne bataya. So I said, say for example, before your ma'am, somebody come to your class and say area of rectangle is length into length, you might be arguing with someone that area of length is length into length. So they were not having any physical idea of how the area of rectangle is length into breadth or the unit square of like that. So when we are going off this, how Praveen sir was talking of the historical perspective of the any topic or say the calculus even, I come to this one also. That's, see, when we were doing that research, we related with that our classrooms also. In classrooms, wherever it's a procedure-based finding out the solution of a question, teacher as well as a student is in a comfortable domain. When you were talking of content challenge in classroom, what I observed, it is when you are talking of limits, when you are talking of continuity in not at some point in some interval, if you have to find this particular value of limit, or you decided whether function is continuous or discontinuous, they have been taught a procedure. But nobody is talking of behind the concept in classroom. I'm not generalizing it, but in majority of the cases, when we are observing a lot many schools and classes every day, in classroom, focus is shifting on how question can be solved. See, in 300 BC, Confucianism, it was said, if I hear, I forget. If I see, I remember. If I do, I understand. In classroom, in classes of calculus, I rarely find any visualization in our classrooms. See, I am talking about a different India. In your classes, it might be happening. But in classroom, there is no sort of visualization or say that technological involvement of, I believe, so many of our teachers, they have not understood even the word MATLAB. Or I think a very rare percentage is using GeoGebra or some sort of thing. So what we are focusing, decide sin 2x is increasing or decreasing in 0 to 2 pi. Well, no problem. But at the same time, I'm not talking about the complex functions, even though some sort of functions, those can be done, even though with chalk and board. It's not happening that at the same time, if I draw it and I draw sin 2x, I can show it that now it is increasing, now it is decreasing, why I say it decreasing, why I say it decreasing. In the same way, there are two aspects, when it is delivering the concept and at the same time, when it is the application. These are the two things, ma'am, where teacher is having a content challenge issue, what we observe. Because when we conduct training programs on part of SCRT, before going for the training program, we do a need analysis. Those who are the participants, we ask them through some Google form or some sort of another thing, that what you want to be done in this program. What are the challenging issues for you? What are the concepts you want to be addressed in the training program, so that we can manage the program according to you, the content part. Most of the time, these two particular domains are there, concept orientation and its application. When it is procedure-based things, find out the differentiation of this thing, to do it. Likewise, the integration process, when they go to area, see, when we say how to teach or say why to teach, see, calculus, as far as its application is concerned, it's enormous. Everyone can find a lot many applications of this, even though in everyday's life. See, I am coming from airport, and every moment, this Google map is telling me, you will reach in 49 minutes, you will reach in 45 minutes. Sometime as per my speed, it increases the time. Sometime it decreases the time. I am improving the quality of pictures. I am downsizing or increasing the pictures what you have taken. Everywhere, even the design of this phone, it needs calculus. Means everywhere, it's enormous. But their applications in real life, their historical perspective, what ma'am was saying, the storytelling approach, all these are missing in our classrooms. It is going away. I'm coming to classroom. I have a formula or say theorem. I write it down, and in some case, I'm doing good. I feel that I should make a proof of this, which is given in my book. And after doing the proof, I come to the book, open the exercise of that, and I start to solve the questions. And when you go to exercise, what type of questions you have there? I don't think the questions are taken from some real case studies or say the standard functions or some, they are highly imaginative, highly type of mechanical type of question. You will find questions, differentiate e raised to power sine log under root x square plus plus plus, जो कुछ मेरे मन में आया मैं लिख देता हूँ, and then I say differentiate it. Why? Why I am going to do that? Child needs to be convinced, why should I learn this? If I am not convinced, see, it is said, if anybody is ready to learn, you can teach him. If I am not ready to learn, you can't teach me anything. So, focus is not make him or her ready to learn the thing. Not that contextual aspect, but even though in gradual development of that subject also. And in training programs, the teacher's orientation, the very first thing, what ma'am was saying, no teacher believed that he could be wrong. And at the same time, they are I'm not generalizing, don't take it in that way. Most of them, they are not ready to accept it that we have to learn something more. Yeah. We used to say in training program, just for joking apart, कि गवर्नमेंट के सेटअप में जिस दिन पढ़ाने का काम मिलता है उस दिन आदमी सबसे पहले पढ़ना बंद करता है. And after that, if you come to the training with a different mindset, those who are training them, they are also questionable. I meet people from universities, colleges, ma'am is also here. They might be thinking that the students, those who are coming to them, they are not well up to their expectations. But at the same times, colleges and universities are not hand-holding the schools. There is a disconnect between them. If colleges like this university is doing here for school teachers today, if colleges and universities people come forward to handhold the schools, definitely they will also be benefited with that. Not just the school.
Yeah, my kids, I always call them my kids. They tell me that if you would, this is my qualitative feedback, that if I would have taught them at school, then probably they won't have left maths at 10. So I think what he's saying is correct.
See, in most of the cases, you cannot make the experiments. If you are giving chemotherapy to a patient, one doctor cannot make an experimentation on a patient, no? What do you have to do? You have to make some mathematical model for that. No? When you are talking about future, predicting future, in most of the cases in real life situation, it is based on mathematical modeling. Everywhere, calculus is needed. In most of the mathematical models, in optimization of the situations, maybe optimization of anything, you need calculus. In biology, physics, chemistry, you see, everywhere, all around us, there is something is changing. And anywhere instantaneous changing happening, calculus is happening there. So, one teacher, when he or she needs to be innovative in a case, he or she has to make the class livable and lovable in that. Otherwise, the situation arises, I don't have data of other states, I have shared you, only 15% opted. And any society, any country, those who want to make a good progress in any sciences or any type of, so even though in social sciences, they cannot afford this, 15% in mathematics, if our generation is opting for it. I'm talking about a different world. That's happening in India, might not be happening in CBSE schools or IB or ISA schools, but this data could be worse if you go to states also. This was from Delhi, what I told you. So when we are going to deal with this type of situation, it's not the child who matters, it's the teacher who matters. And teacher is coming after certain recruitment process. He passed that, but after that, the in-service orientation, the teachers, I know when I joined this job, what my status was there, and how much I learned during my teaching experiences. I think most of the mathematics I learned when I was teaching. So in service training programs, now NEP says 50 hours for a teacher every year. I'm hopeful that every school will follow this. But at the same time, what my honest suggestion would be there. See, in every state, there is a State Council of Educational Research and Training. And in India, in every district, we have a District Institute of Education Training. They are doing on their part. I don't want to comment on that, how they are doing and what they are doing. If in every domain, every part, private sector or they say the corporate sector, they have done so well, they are competing all over the globe, why don't these people come to train the teacher forefront? They can have that quality product, that quality content, that quality resource person. See, in training program, what's the main function? If you have a good resource person talking here, then rest of the things are, doesn't matter. So, what I'm happy to see, what happening here for the last 3 days, 2 days, third day is there today, I think. But this is the very first time when I came across such a, in Delhi, for last 12, 13 years, I have been associated with training programs. And Delhi is the state which is investing, I think, उससे ज़्यादा investment teachers की training पे इंडिया में कहीं खर्च नहीं हो रहा है. I have been trained in Cambridge, in Moscow, in Finland, being a principal. But in Delhi also, that quality of that training, that's also questionable. I'm not saying it would be perfect if it is done in other way, but it could be better, it could be improving. So I hope classrooms to get better. They could be interesting one for children. Again, it won't be of any use for any kid if he is simply solving the problem. See, solving the questions parted in textbooks, it's not understanding mathematics. That is simply a process. I told him, ये chain rule है. Just learn some formulae, learn differentiation of some basic function. Apply this, you will get differentiation of this. And he doesn't know, ये जो आया है इसका मतलब क्या है. So till that time, it doesn't being that practical, it won't be of any use. And people like her, they will be in problem all the time. Thank you.
Yeah, I just wanted to thank all the panelists, and thank you so much, Praveen. I'm not sure what the time must be at your end. Thank you all for being with us.